Good morning, everybody. My name's Dawson Knorr. This is Adam Connors. There's only two of us, so we're going to be doing a lot of walking back and forth to change our slides. Like Mike Tweed said, we are the design of the gait trainer braking system. So a little bit of background on our project. Our sponsor for this project is Lifescape. We're mainly working with the office down in Sioux Falls, and that office mainly deals with medical rehabilitation and disability support for clients of all ages. The problem statement they gave us for this project is to design a parking brake system for a gait trainer that works in conjunction with safety features on the gait trainer, and then with improvements upon the user interface and then the brake activation too. And then the motivation behind this project is the office down in Sioux Falls. They have 190 patients in the last 3 years that they've sold gait trainers to. So there are definitely a lot of people that are affected by this just in our area alone.
So what is a gait trainer? Specifically, it is a walking aid for children, and the model we received was an R82 crocodile made by ETAC. ETAC produces 4 different sizes, anywhere from a size 0 to a size 3. Lifescape gave us a size 2. It is an older model. They do have some newer ones, so there might be some differences. However, they all contain an anti-rollback technology in the bottom right. Right now it is disengaged, but it only allows movement in the forward direction when it is engaged.
So ETAC, the company that makes the gait trainer, does make park and brake systems for the R82 crocodile. Lifescape, they don't like this for multiple reasons. One, it replaces that anti-rollback, so you can't have both safety features, just one of them. The second one is the brake handle. It mainly relies on grip strength, doesn't allow for use of all of their clients. So they really like to widen the range. And then the total cost of that is pretty spendy at $160.
So for our project, we had to come up with some objectives for Lifescape. Now, the first one, Lifescape wanted it mainly manufactured in-house. Biggest constraint with that is they've already bought a couple 3D printers, so we are stuck with using what they've already bought. Our second objective is to design more ergonomic handle that more of their clients can use. The biggest issue with that is they have anyone from a toddler to preteens and teenagers. So you're looking at a very wide range of abilities. And our last objective was to design a locking brake that integrates with the anti-rollback. The issue with that is there is limited space, and material selection that we have does not help that. So with our manufacturing, like I said, Lifescape does already have a couple of 3D printers. The first one is a Prusa Mini Plus. It's a fairly basic and budget-friendly printer. It's fairly limited compared to their second printer, which is a Taz Workhorse. It's significantly more expensive at around $3,000. But it does allow for more filaments. But because the Prusa is limited, we chose that as our limiting factor because we want all of our parts printable on either printer in case one of them were to break. So the first thing we needed to do was narrow down our filament choices. The first thing we did was use a decision-making matrix with PLA as our baseline because it is the most common filament and it's what Lifescape already has a bunch of. So we used this to narrow it down to 3 different choices with PLA, PLA Pro, and PET-G. We used a grading scale from 1 to 5, with 1 being the worst and 5 being the best, to figure out which one we would choose based on the criteria that we chose and our sponsor chose, and the weights that we came up with for each of those categories. We came out with PLA Pro as the best choice.
So moving on to the second objective, and then to address this, we need to redesign the entire brake handle and the brake activation method. So first we took a look at the system that ETAC produces and sells. And they had an input force of around 5.5 pounds. And then we did some research on the users themselves with average grip strength at 6 years old being around 19 pounds. And that number was given to us by Lifescape. So we are going to use that for, a max force for our brake engagement. And then the last thing we looked at for their system is the mounting space on that handlebar. Their handle only takes up 8% of the total length of handle. So we're going to use that as a goal for our project too. So for the design of the handle, we use the first 4 designs just to kind of get our ideas out, and then talk to our sponsors and see what they liked and disliked about the brake engagement. So this first one, you can see we used a kind of a gear shift like brake engagement. So the user is going to grab that knob, push it forward, and then slide it out to the side to lock the brake in place. And then the reason they like this is because it relies on a wider range of muscles. So if a client doesn't have the use of something, then they'll still be able to use this. Future improvements upon this one, mounting and assembly. The assembly of this is fairly complex, and then we don't have any mounts on this either. So with that in mind, we streamlined the design, went with more tubular style, utilizing rotation, so it still keeps the benefits of that gear shift. I'll push it forward and then rotate it out to the side instead of sliding. And then it just kind of reduces the overall size of the handle. This handle is mounted directly to the handlebar. Do you want to slide? You can see that in the far picture to the right there. And then the cable routing, this is the pod that slides into the tube. The cable that we are using is a standard brake cable. That's what ETAC uses too. And so the end of that will fit into the left picture there, that yellow square. The end of that will fit into that slot, and then the tube will slide into, or the pod will slide into the tube. The only downside to this version is the mounting length. It takes up more than 1/3 of the entire Gait Trainer handlebar. So with that in mind, we moved the tube out away from the handle. This solved that problem. With this mounting, we are at less than 8% of the handlebar, so that meets that goal for the handle. However, it does add a potentially long lever arm to the mount. And then with that in mind, we did do some simulations on this in the worst case scenario. So we applied a force at the very end of the handle and fixed the handle mounts, and you can see in the yellow circle there, that's where stress concentration was. We use this just to kind of predict what our testing might look like. And then to our testing, we did the same thing. We mounted the handle onto the Gait Trainer, and then we applied a load at the very end of the handle. Here are the results for that. Kind of sad. We only got around 40 pounds, which is less than half of the max weight of our size of Gait Trainer. However, you can see that it did break at that predicted stress concentration from the simulations. And then on the other side here, you can see a little bit of plastic deformation in the handle mounts and the bottom of the tube. We also did a handle mount threshold test. So we wanted to see what our handle mount could, what load it could withstand. So we torqued the screws to 4 different settings, and then applied a load at the farthest lever arm for the handle mount, excluding the tube from this test. The results for that, for the torque of 10 inch-pounds, we got a very large standard deviation, very unreliable results with the peak at around 80 pounds, and then the low is 40 pounds there. However, once we got to 25 inch-pounds, our standard deviation went down to 3.5. And then our peak does get around 97 pounds, which is very close to the max weight of the user. So with those testing and simulations in mind, we shortened the length of the tube, reducing the travel of the handle knob and the pod. That shortens the potential lever arm, and then we did some more testing on that, or simulations, sorry. For these simulations, we varied the wall thickness of the tube to see if that would increase the strength of our part. We simulated it at a wall thickness of 0.1, 0.125, 0.15, 0.2, and 0.25 wall thickness. And you can see a large jump down there in a wall thickness of 0.15. That's mainly due to the fact that more of the stress is in the handle mount than the tube, which you can see in that top picture there. And then the bottom picture is the simulation at 0.25. That high or the peak stress goes from the tube to the handle mount. And then with that, we did some testing on these again. We tested the wall thickness of 0.1 inch, 0.125 inch, and 0.15 inch. The reason we didn't go any higher than that was because at 0.15 inch, we saw a failure mode in the handle mount instead of the tube. So increasing the tube wall thickness wouldn't increase the overall strength of the part. And then at a wall thickness of 0.15, we did see a max load of around 86 pounds. And that will be our handle.
So to fulfill our third objective, we needed to design a new brake mount. So the first thing we did was an analysis to find our required braking force. We had to find the max user weight for the Crocodile, which is 99 pounds, and using our graph, our required brake force is around 55. So our first mount is mounted above the anti-rollback. This was the easiest solution because it doesn't interact with the anti-rollback. There's no need to do any disassembly, don't have to touch it. And it allows for easy assembly. It's very easy to access. You can use basic hardware, nuts and bolts. And it allows the brake pad to be mounted behind the anti-rollback for a self-energizing brake, which just means that the more friction you use, the more braking force you get out of it. But because of the shape of the frame and the material we're using, we would have to use a very high clamping force. And to fix that, we decided to go around the anti-rollback instead, which kept it from rotating and did have to change some of our hardware to match the handle because we wanted to keep the cost of it down, which means that buying in bulk is going to be a little bit better for us. It also provides a much more stable attachment point with more consistent alignment with the anti-rollback, so that way you don't have them turned into each other and possibly touching. So like I said, we wanted our brake to be self-energizing, which means we wanted it mounted behind the anti-rollback. The first brake pad that we had was the pivot point was at the far end, which means that the input force needs to be fairly high to get a good reaction force out of it. However, it does maximize the surface area that does touch the wheel. But because LifeScape has younger users, we wanted to make this a little easier for them. So we moved to the pivot point towards the middle, which does reduce our input force and increases our reaction force at the contact patch. But that brake pad does have a small contact area on the wheel. Our model does show a better contact patch, but in reality, it is not that much. So the changes we made were we added a little bit more length to our second version to make version 3. This does increase the contact patch, but does decrease our reaction force. But compared to our first version, we still have a better reaction force than that one. The reason we increased surface area was it does reduce wear. And when we mounted it, we decided that we should try a different one just to see what would happen with it, which is where we came up with 3.1. It's very similar to 3. It just adds a little bit more curvature to the bottom of the brake pad to increase surface area again. So for our brake testing, we used a simple pass-fail system, with passing being that the wheel slips on the ground first, and fail is the brake slips on the wheel first. We applied around 1.9 times the max user weight to the end of the handle of the blue arrow. The anti-rollback was not engaged for testing because we wanted to test the brake on its own, and we tested on several different surfaces. So for e-tax testing, they do have 3 different settings, and we tested every setting. The third setting did perform the best, with 75% of the surfaces passing and 25% failing. In comparison to our testing, our system only has one setting. It's either engaged or disengaged, which means that all of our settings can be the same across the board for every version that we had. Looking at our forwards direction, we did pass because our brake is self-energizing, so that did validate that our brake did what we wanted. However, in the backwards direction, we did not pass, but with the addition of the anti-rollback, that's not really relevant as long as that is engaged. So with our economic analysis, LifeScape gave us a manufacturing budget of around $200, which means for a set of 2, it needs to be $200 or less per brake system. As Dawson said earlier, e-tax brake system is $160, with 30 of that alone being for shipping. I believe e-tac is actually a European company, which explains the high shipping cost. However, to compare the 2, we had to break ours down into individual parts and add them all up, and we got a cost of around $36.50. It's a reduction of just around 77%. If LifeScape wanted to build brake sets for all 190 patients that they've had in the past few years, it would save them roughly $23,500, which is a very large amount.
And then just to kind of wrap everything up, since we are a second semester project and we wanted to confirm that all of our objectives were met. First, we'll go back over all of them. The first one is the manufacturing in-house. All of our parts are 3D printed and then assembled with screws and heat set inserts. So we did complete that one. The second objective is the ergonomic handle and the brake activation. Most of this objective is completed when the medical professionals of LifeScape are happy with what we have given them. We did hear a little bit of feedback last semester at the expo from somebody who has used a Gait trainer, and they liked the thought of the gear shift brake handle. So we viewed this objective as complete. Same with the third objective. This is just based on the feedback we get from LifeScape too. So our locking brake is integrated, works well with the anti-rollback. They're completely separate systems and will work independently of each other. Are there any questions?
Will the tire wear down before the brake pads?
So the question was, will the tire wear down before the brake pads? They did give us a e-tax braking system and an anti-rollback with the Gait trainer they gave us too. I don't really see any wear on the wheel itself. There is a little bit of wear on their anti-rollback system and their brake too. So with our brake pad, since it is 3D printed, the cost of it is less than $5. So replacement parts for the brake pad, the handle, anything that could break is really cheap. Comparing that to e-tax, where if you do break something on their system, you would either have to contact the company or buy a whole new braking system.
You mentioned that the braking force that you needed was 55. What are the units on that? How is that defined?
Okay, so the question was the braking force required for our size of gate trainer is 55. What are the units on that? And say
How is that defined?
how is it defined? Good question, thank you. The units on that were just pounds, because that's what the spec sheet for the gate trainer that we got gives us is 99 pounds. So what we did a force analysis, a statics analysis on that. We found the X and Y distances and did a moment analysis. So 99 pounds applied at the handle and then fixing the wheel.
I guess so Dr. Letcher's been waiting for me to bring this up. It's a medical device. And I just looked and there are at least, I don't know, 40 ISO standards that apply. Did you guys look at any of those by any chance?
We did not.
Because
No.
it would tell you things like, you know, how those forces that you've been talking about, and so on and so forth. It's class 1. You know, which means you don't have to tell the FDA about it, which is a good sign. But it also means that if ETAC's gonna build this thing, they're gonna have to build it to those standards. I mean, ETAC Lifescape, they're gonna have to build it to those standards. And it's gonna be a little more complicated, I think, than you described. I'm surprised Lifescape actually wants to make these things themselves, but apparently they do, right?
Yeah. So the question.
Capability of doing that?
Sorry, say that again.
Does Lifescape have any capability of doing that?
Yeah.
3D
So
printers, et cetera,
Yeah.
et cetera.
the question was, are there any ISO standards
There are ISO standards.
that are relevant to this? Lifescape didn't let us know or tell us about any of those standards.
I'm not surprised.
They do have 3D printers in-house that are capable of printing all of the parts that they would need for our braking system.
I can tell you the numbers of the ISO standards later.
Okay. Yeah.
Yeah, so you have that gear shift type of braking mechanism there. So you also have the handbrake, like the bicycle brakes on the device as well, or is this replacing the other?
No, our system completely replaces the ETAC system. We wanted to get away from the more bicycle brakes just because it relies mainly on grip strength.
Okay, but so I guess from a user's perspective, as far as, you know, like what does the person have to do? Like, do they have to remove their hand from the handlebar to move the gear shift?
Yes, they do. Yeah.
Okay. The feedback was that was positive?
They really liked the gear shift, and I mean we went through multiple different handle brakes with them, and they picked that one as their favorite. So. Yeah.
Have you had anyone that actually uses a gate trainer like test it?
We did send them a handle. I haven't heard anything back from them if they've actually had anybody use it. I think they might have just put it on one of the gate trainers that they have there, and if somebody wants to come in and use it.
Thank you very much.